Okay, so good morning once again to all of you. So we are all, I think now it's a final lecture of this semester, okay, of MM681 course. Okay, so I think we had so far 23 lectures, and this is today's one is the 24th lecture, I guess. Okay, so I hope this course met your expectations. Okay, so I think we'll discuss towards end, okay, about the course, okay, kind of what kind of feedback we can, okay, you have about this course, okay. So I think I think finish today's lecture. In my previous lecture, we had discussion about, okay, severe plastic deformation, okay. So there are various methods are available, okay, by which we can induce very large amount of strain under hydrostatic, okay, pressure, under hydrostatic pressure, along with a regular, we have to apply some force and also have a hydrostatic pressure that can lead to, okay, significant grain refinement. If we take 100 micrometers of grain size, I can get it down to 1 micrometer of, okay, or 200 nanometer, depending on material to material. The final grain size is going to vary. Okay. So by inducing large amount of strains, we can actually retain the shape change. If we can retain the okay, the shape of the material. So that process is called severe plastic deformation. Okay, various techniques have been developed. Okay, about 100 techniques are there. Okay, with some slight variations, okay, in the basic methods. The basic methods are basically equal channel angle pressing, high pressure torsion, okay, multi-directional forging, accumulate roll bonding, repetitive corrugation and straightening, and there are combined action of, okay, some of these, okay, you can have combined action of SPD techniques. So we had discussion about ECAP, HPT, MDF, ARB, and RCS, and we also had discussion about mechanism of grain refinement when material subjected to severe plastic deformation. Okay, so there are five basic rules, okay, which usually applied, okay, for the grain refinement, okay, under severe plastic deformation. The first one, we must do deformation, okay, below zero point 0.5 times of melting point, where we can, okay, we can retain the dislocation density, high dislocation density. Higher dislocation density can lead to, okay, finally high angle fine grain sized microstructure. At the same time, okay, we should, okay, apply very large amount of strains for getting a homogenized fine grain structure. So we need to have typically true strain of, okay, 6 to 8. By then we can get a very good, okay, okay, almost uniform distribution of grain size, okay, throughout the material. And we should also induce some hydrostatic component so that the material will be still in solid state. Okay, at the same time, the diffusion can be minimized. Diffusion can be minimized, and defects like cavities, voids can be closed under hydrostatic pressure. Okay, then we need to have vorticity. You have to create a vorticity of a metal flow. The metal flow has to be, okay, should be randomized always, so that it can, okay, apply cross loading. We can actually get a very, okay, fine grain size in the material. And the fifth one, depending on stacking fault energy, okay, the grain refinement is going to change. Lower the stacking fault energy, finer the grain size we can get by severe plastic deformation. Okay, these are the, okay, basic rules what I discussed. Okay, so this, I think all these things were discussed in the previous lecture. If there are any doubts, please let me know. Are there any doubts about this severe plastic deformation? No. Is it clear?
Yes, sir.
Okay, so today's, okay, topic is basically related to intermetallics. Okay, so there are, okay, various types of intermetallics are available. Okay, The name itself indicates, okay, compound, okay, it's a compound which should form between metals, okay. So there is a standard textbook, okay. There are, I think, Westbrook and Fleischer. They have written three, I think, books. Okay, one of them is a basic thing, okay, related to mechanical properties, okay. You can see, okay, this book is very much useful if somebody wants to have more understanding about intermetallics, okay. So the name basically indicates that, okay, a compound which forms between metals, okay, it's called an intermetallic. Can anybody guess, say some different types of intermetallics what we can see in materials? What are different types of intermetallics we can come across? Any idea? Some intermetallics like
Yes, sir. Cementite, nickel, aluminide.
cementite. Yeah, it is not really intermetallic, but yeah, some people consider it as intermetallic. Okay, that's a hog face cementite. Okay, carbide. That's a metal and a carbon. Okay, a carbon is not necessarily a metal. Okay, we do not consider, some many people do not consider carbon, okay, nitrogen, those are not like a metals, okay. But still, okay, in this textbook we may figure out, okay, that also has one of the, yes,
So this
nickel aluminide.
nickel Ni3Al and
Yeah,
gamma titanium aluminide kind of thing.
yeah, aluminides, okay. We do see, okay, titanium aluminide, nickel aluminide, iron aluminides, okay. Aluminides are very famous intermetallics, okay. Is huge amount of research is going on, okay, developing, okay, intermetallics between, okay, metals like a iron to aluminum, okay, nickel to aluminum, titanium to aluminum, these aluminides, okay. We do see, also see zirconia, okay, zirconium compounds, okay, Al3Zr, okay, compounds between aluminum and zirconium. There are various compounds, okay, around, I think, 20 to 30,000 compounds are available. 20 to 30,000 intermetallic compounds are available, okay. So the basic classification, okay, and how these intermetallics form, okay, whenever there is a violation, you know that, okay, Hume-Rodri rules. What is Hume-Rodri rules tells? Hume-Rodri rules are applicable to what? I guess many of you know that, okay, okay, Hume-Rodri rules.
Solid solution.
Yes, sir.
Yeah,
Solid solution.
solid solution. Okay, whenever there is a violation of those rules, okay, Hume-Rodri rules, that means, okay, there is a possibility of forming a intermetallic instead of a solid solution. Instead of a solid solution, intermetallics are going to form. Okay, so that, okay, as a, whenever, okay, we have basic. What are the basic rules of Hume-Rodri rules? Any idea? What are,
It need to
Sir,
have
there are four
solid
rules total.
yes. Okay.
One is related to the negativity. When
Negativity, electronegativity. Okay.
yes, sir.
Then
When they are high, then compound will form intermetallic.
yes, yeah. So that, yes. Next,
Atomic
what is the
radius.
size factor? Okay,
Yes,
size
sir.
factor. Yes, yeah. Then what else?
Electronegativity, sir.
No, I think already mentioned electronegativity. Yeah, that's it. And valency.
And
Okay, valency. So this, okay, whenever there is a violation of these rules, one of the, at least one rule gets violated, we get a, okay, intermetallic formation of a intermetallic can be expected rather than a solid solution. Accordingly, okay, we do have different types of intermetallics. Okay, valency compounds, okay, electron compounds, size factor compounds. These are actual intermetallics. So interstitial compounds, okay, if it, okay, between metal and interstitial element like carbon, nitrogen it forms, okay, those are called interstitial compounds. Hag phases also called. So whenever there is a valency, okay, electronegativity difference, okay, greater than zero point 0.4, we do see this type of intermetallics are going to form. Okay. Electron compounds based on E by ratio, based on E by ratio, okay. So that actually can give rise some type of compounds, intermetallic compounds. Similarly, size factor compounds, Lavis phases, okay, we do see, okay, Frank Casper phases, okay, very, I think many of us know in stainless steel, we do see formation of sigma phase, which is a detrimental to the overall behavior of a material, okay, between iron and chromium, okay. This is sigma phase is very, okay, dangerous compound in, okay, it has to be avoided, okay, in stainless steels. Okay. So we do see some of the compounds are very much useful, some other compounds are okay detrimental to the overall behavior of a material if those are present in a metallic materials. Okay, if they are individually present, those are called bulk intermetallics. Bulk intermetallic materials. Some of them are considered as a structural intermetallics. There are some materials intermetallics which can be considered as a structural ceramics like titanium aluminides, nickel aluminides, iron aluminides. These are actually structural intermetallics. Okay, so one can classify the intermetallics into valency compounds, electron compounds, size factor compounds, and interstitial compounds. Okay, so when we talk about there are other classification about the intermetallics. Okay, based on phase diagram, the existence of a compound can exist like a stoichiometry base, single a single composition. If you take a phase diagram, temperature versus composition, if there is a single composition, that is typically called Daltonic type intermetallic. If intermetal compound exhibits over a range of composition, or a range of a composition, that is called Bertholide type compound. And there's another thing we see, ordered disordered transformation. Okay, those are called Kurnikov type intermetallics. Okay, if I see one example of a nickel between nickel and aluminum, a phase diagram, if I take a phase diagram between nickel and aluminum, okay, we do see different types of compounds, Ni3Al, okay, NiAl, okay, NiAl3. So there are various types of compounds can form between nickel and aluminum. The most popular compounds, Na3Al and NiAl. Okay, so we do see NiAl is type A. Okay, it's exhibiting over a range of over a certain range of composition. It's still NiAl. Okay, so we do see some higher amount of aluminum or a lesser amount of aluminum. Okay, so if it is a atomic percent, if I take and like 50 nickel 50 atom, it's supposed to be, if it is stoichiometry compound, then we should see only single line, but we are seeing a existence of this compound over a particular range. Okay, so that means we can see aluminum rich or a nickel rich kind of compounds are going to be present in a NiAl. If I see Al3Ni, it's like a single. There is stoichiometric compound. Okay, so we do see half stoichiometric compound and stoichiometric compounds. Okay, in the intermetallics. So accordingly, people have given different names. Okay, so these are the kind of different classification of intermetallics. Is it clear what I'm saying?
So
Hello,
this
sir.
C-type intermetallic compound, this daltonite, is it, I mean, any examples of, because I have never come across such type.
No, daltonite is like a single. Okay, no, there won't be any off stoichiometric compound formation. It is a single compound. Okay, particular composition only. Okay, it will not deviate from its composition. If you look at here,
But
Al3, it is a single. Okay, this doesn't have any solid solution. These are like a solid solution intermetallics. People call
okay.
it. Okay, these are like a intermetallic alloys. Okay, nickel rich or aluminum rich. We may see. Okay.
Hello, sir.
Yes.
Sir, is there any composition range that we have to have in a compound for it to be called an intermetallic, or it
No,
can
if,
have
you
any
see,
composition range?
if I want to have an NiAl, I should have typically 50% nickel, 50% aluminum. Am I right? If I take
Yes, sir.
Ni3L, how much atomic percent if I should have?
Should have more of nickel, less
Yeah, one by
aluminum.
four. Okay, 1/4 aluminum I should
Yes,
have,
sir.
and 3/4 nickel should
Yes.
have. Okay, then only we expect this compound formation. But interestingly, some intermetallics can exist over certain range of a composition. So those are typically called intermetallic alloys. Okay, so we do see some nickel rich, aluminum rich compounds are going to present in this case. Okay, so that means at least you should have a this much composition locally to form a this kind of intermetallic. Okay,
Okay, sir.
whenever nickel and aluminum come in contact, for example, when there are 3 atoms of nickel is available for one atom, then we expect a Ni3L formation at that region. Okay, but it requires some temperature. Okay, any reaction requires some free energy change. Okay, We need to give some thermal energy, then only we do see formation of these compounds. It's a chemical reaction, okay? A compound is going to form by chemical reaction, simply. Is it clear?
Yes.
Okay. So this is a kind of, okay, two different type way of classifying the intermetallic compounds. If I look at structures, okay, typical structures, okay, intermetallics will also have their own okay, crystal structures. For example, we have iron. Okay, iron can have a BCC, FCC, body centered cubic, FPS centered cubic. The copper, FCC, face centered, magnesium has SCP. So like that, even these compounds, intermetallic compounds, will have their own crystal structures. Will have their own crystal structures. Okay, if I take NiAl or FeAl, okay, or CuZn, okay, these will have, okay, structure, okay, similar to BCC, similar to body centered cubic. If you look at here, okay, I have, okay, if I take 50% atoms of nickel, okay, 20% of aluminum, 50% aluminum should be there, 50-50 should be there. So if you take, okay, typically it is going to have a BCC kind of structure, but okay, it is called BCC derivative structure. BCC derivative structure. For example, if I take, okay, aluminum atoms at the corners and the nickel is occupying center, okay, body centered position. Okay, if I take, okay, we are going to have a, okay, two interpenetrating cubic structures. Okay, it is lattice structure is basically simple cubic. It's not a BCC. It is a BCC derivative. Okay, if I take individual atoms, how they arranged aluminum atoms, if I take, it is a simple cubic. Similarly, nickel, if I take 8 cubes, okay, I'm going to have a nickel is going to have a simple cubic structure. But if I see, okay, NiAl together, it is look like a, okay, BCC, body centered cubic. So popularly, these are actually, okay, there are different ways, okay, people report, okay, by using a, okay, structure buried notation, okay, or Pearson symbol. By using, okay, this is a kind of crystal structure, okay, structural notations people use. Intermetallics, many times people use structure buried notation. Structure buried notation. If you typically this NiL, FeL, CuZn, these come having structure B2. It is simply called B2 compounds. These compounds are called B2 compounds. Okay. Here the Pearson symbol CP2. Okay. C is a cubic. Okay. P is a primitive. Primitive means simple cubic. And we are having a two atoms. Two atoms. Okay. In the crystal. Okay. Lattice. Is it clear about the kind of, okay, notation, crystal structure notation about, okay, B2 type of compounds? Okay. So there are various examples I've given. Okay, NiL, FeL, okay, nickel aluminide, iron aluminide, copper zinc, okay, compound, and cesium chloride. These are all under common category of B2 intermetallics. Okay, any doubts here?
Sir, so in the last slide, in the phase diagram,
Mhm.
like for NiAl, we have a range of nickel, while for Ni3L, it is very small.
Hmm.
So, what exactly does this signify? Is it five that does this mean NiAl is more stable than Ni3Al or no?
No, it's not like the defect. Okay, the particular crystal structure, what type of defects are going? I think we'll discuss. Okay, we'll come to know that, okay, shortly.
Okay.
It is depends on the defects. We need to have, okay, accommodate one of them aluminum rich or, okay, nickel rich. We need to have some defects. Okay, then only we can accommodate. Okay. Some of the structures will not facilitate so much defect concentration. Okay, so this is one of the popular, okay, B2 compounds. Like that, we also another thing called L12. Okay, L12 structure buried notation, Ni3Al, okay, Ce3Au, okay, that's titanium platinate compounds. Okay, these come under category of L12 structure buried notation. Okay. So look at here, it is a FCC derivative, face centered cubic derivative. So if I look at, okay, if I take Ni3Al, okay, for example, or Cu3Au, okay, that means three atoms and of copper, one atom of gold should be there in a single unit cell. Okay, so that basically comes if I arrange, okay, gold atoms at the corners of the cube and copper on the face centered positions. So we are going to have one effective atom of gold and three effective atoms of copper. Similarly, nickel, if you take nickel aluminate, aluminum atoms are going to occupy corners and face centered is nickel. Okay, so if I look at here, so this is basically all together we are having a four atoms in a unit cell. But individually, if I look at each one of them having a different primitive cubic. If you take aluminum corner atoms, you only consider corner atoms, so I'm going to have a cubic. Similarly, if I consider this nickel atoms, face centered atoms, will be having it's not a face centered cubic. It is a derivative of a face centered cubic structure. So that's why actually we do see it's a cubic C, Pearson symbol C, and P is a primitive. P is a primitive, and four number of atoms are present in a material in the unit cell. Okay, so this is how actually the it is a derivative of FCC, but it's not really FCC structure. So L12 is very popular. Okay, there are several compounds come under category of one of the most important one is one you consider is Ni3Al. Okay, so people have simplified it in order to see what type of compounds we do see. What are the BCC derivatives? What are the FCC derivatives? What are HCP derivatives? Okay, so if I look at here, BCC derivative structures. Okay, if I take eight cubes, arrange eight BCC cubes if I arrange. Okay, so I have a corner atoms alpha. Okay, one cube will be having beta, centered body centered one. Another cube will be having gamma if you consider the locations of atoms. Okay, the B2 types, AB type compounds like NiAl, FeAl, these are going to occupy, A atoms are going to occupy alpha sites, B atoms are going to occupy beta and gamma sites. Okay, those are actually AB type compounds, but still it is a derivative of a BCC. Okay. Similarly, we also see A3B type, but not necessary to be L12 L12 crystal structure, not necessary to be L12. This can also have a BCC derivative, for example, Fe3Al. Okay, it is different from Ni3Al. Okay, Fe3Al is going to have a cubic structure. Okay, but we are going to have 16 atoms. Okay, how are they going to present? A atoms going to occupy both alpha and gamma sites, alpha and gamma sites, and B atoms going to occupy beta sites. That means we will have a big unit cell. We are going to have a big unit cell for A3B type BCC derivative structure. Similarly, we also see L21, not L12, it's L21, A2BC type compound. Okay, so three elements are participating in forming a intermetallic compound, Ni2Al Cu2MnAl. Okay, so these are kind of examples, multiple three atoms, three different type of elements participating in forming a compound A2BC. Okay, so those are called actually L21 structure. So A atoms going to occupy alpha site, B atom going to occupy beta sites, C atom occupy gamma sites. So if I take 8 body-centered cubes, and if we know the locations, if I identify alpha as a corner, and alternate if we have beta, gamma centered body-centered positions. So how they are going to be occupied by particular elements? So we can get a BCC derivative structures. Okay, we also see FCC derivative structures like that. Okay, L12 we already discussed. Okay, Ni3Al is a best example, A3B type. So corner atom is going to be occupied by one atoms. Okay, so here for example, if I take like this, we have actually face centered. One is actually top and bottom face centered. We consider as a beta. Other face centered gamma sites and alpha. Okay, in case of L12 structure A3B, B atoms are going to occupy the alpha sites. In case of A atoms occupy beta and gamma sites is simply called L12. We also have L10, L10, CuA, is popular compound, and TAL, titanium aluminide, and copper, gold compound. Okay, look at here, corner atoms plus, corner atoms plus, top and bottom face centered, top and bottom face centered are being occupied by particular atom A. Okay, then we have, okay, other face centered face centered positions are being occupied by B atoms. Okay, this is going to give you, okay, tetragonal structure. Okay, though it's a B, okay, FCC derivative, okay, if individually we consider, okay, it is going to have a tetragonality. Okay, that's actually T. Okay, it's not a cubic one. Okay, it's a tetragonal. Okay, because your positions of atoms can distort the, okay, lattice, okay, parameter. So that basically lead to a tetragonality. So AB type of compounds can form with effective number of atoms 2 in the material, okay, in the unit cell. So this is a kind of, okay, where these are structure Barrett notations people use. Okay, the most things we what we discuss is really B2 type compounds and L12 compounds. Apart from that, we also see other type of compounds, L10, titanium aluminide, and, okay, copper gold. Okay, these are kind of different
Sir.
way of, yes.
Sir, in L1, 2, I
Hmm?
mean, what is the exact significance of 1 and 2? I mean,
No,
this
there is no significance. Okay, that structure Barrett as they get taken up randomly. Okay,
because actually, sir, 2 is generally written as a subscript actually.
subscript, yeah.
So, does this have any connotation or?
No, I think it has come, okay, initially randomly they picked up. Okay,
Mhm.
there's no significance for L. What is L? There's no significance.
Because I tried actually in so many places, I could not get a clear cut, what do you call it, reasoning why it's named like this.
No, I think I
So,
didn't. I too didn't figure out. Okay, I tried it. Okay, several places, but I couldn't figure out. Okay, there's no, okay, clear physical significance of this, okay, number and letter
mhm.
here.
Okay, okay.
But actually, there is a, I think A B C. There is a notation. Okay, people use A B C. The B2, B is basically, okay, body centered base thing. Okay, they use so B2. So, but yeah, L1 suddenly, I don't know how they brought this L1 to L10, but it suddenly it came, okay, without any, okay, proper connotation behind this thing. So is it clear? Because there are other FCC
Yes.
derivative structures we do see. Okay, DO22, okay, DO23. Look at here the complexity. Okay, AL3ZR if we take, okay, it is going to have a, okay, a big unit cell, okay, very big unit cell. Okay, so this kind of arrangement we are going to see. Okay, so the lattice parameter is going to be, okay, going to be very different. Okay, so this is called, okay, T, okay, tetragonal, okay, I, okay, 1 6. So 16 atoms are going to present in a unit cell. Okay, here is for example DO22, okay, we are going to see 8, okay, effective atoms in a unit cell in a particular, okay, in a fixed unit. This is a complete thing is a one unit cell. Okay, it's going to have six, okay, 8 atoms per unit cell. Okay, so there are actually complex crystal structures are going to exist, okay, for some type of intermetallics. Okay, one example I given Al3 jet are very, okay, look at here, we do have a very big unit cell, okay, with 16 atoms, effective atoms in a unit cell. So similar, okay, BCC, FCC, there are also SCP derivatives, okay, hexagon close packed derivative structures, okay, DO19, okay, DO24, okay, so Na3Ti, okay, nickel titanite. So these, okay, are going to have a SCP derivative structures, SCP derivative structures, okay. So there's another important compound, okay, NB3SN, okay. I hope all of you know about the importance of NB3SN, okay. I hope everybody knows about NB3. What is the specialty of NB3SN? Any idea? No? Yes or no?
No, sir.
Okay. So this is actually one of the, okay, superconducting compound. Okay. Best known, okay, superconducting compound NB3SN. Okay, so NB3SN is going to have, okay, body centered and face centered positions. Look at here, tin atoms are going to occupy, okay, corner atoms and body centered position, and niobium is going to occupy, okay, two atoms in a face, two atoms in each face. Okay, it is going to occupy two atoms in each face. Okay, so it's like a very big, okay, once you have more atoms, okay, and different type of atoms, the lattice parameter is going to increase. Okay, it's not a HCP derivative, it is a combination of BCC and FCC. Okay. It is going to have a BCC and also HCP. Okay, that's not HCP, BC, FCC. FCC position, some kind of face centered positions it's occupying, but not exactly face centered. Okay, there are two, okay, atoms on faces. Okay, so as a result, okay, people call it as a A15 matrix. Okay, it is going to have a cube, or finally it's going to have a cubic and a primitive unit cell considered as a primitive, and 8 atoms. The unit cell is going to have a 8 atoms. Okay, so basically, okay, when you talk about, okay, intermetallics can exhibit various types of crystal structures. Okay, some of them are much more complex than what you can visualize. Okay, some of them is not easy to visualize also. Okay, such a complex crystal structures are, okay, are present for certain intermetallic compounds. Whatever I showed you, some simple things and which have some importance also. Okay, I given some examples which have some importance. Okay, so we do talk about, okay, nickel aluminides, okay, iron aluminides, and titan aluminides. So I've taken some examples, okay, which are popular compounds. I've showed you some, okay, some of their crystal structures. Okay, so when you talk about intermetallics, like a metals have a some crystal structures, will also some defects. Okay, we also already discussed. Okay, so metals will have defects. Okay, like metals also, intermetals also going to have some defects. One thing we had discussion, okay, earlier, I think, anti-sites. Okay, so we know that, okay, Ni3L, if you take a Ni3L, it should have, okay, this kind of, okay, arrangement. Corner atoms should be occupied by aluminum, and face-centered positions is L12. Okay, L12, we should have a face-centered position should be occupied by the nickel atoms. Okay, due to some processing, okay, effect, okay, we may see, okay, formation of this anti-sites. That means actually additional. Okay, so we look at here, okay, one, okay, nickel position, atom position has been occupied by the aluminum. Okay, that means it became a aluminum rich compound. Can also, we may also see, okay, one, okay, corner atom of aluminum has been occupied by nickel instead of aluminum. So that can lead to a nickel rich Ni3L compound. Okay, due to some, okay, conditions, processing conditions, that can lead to formation of anti-site defect in intermetallics. That can lead to, okay, formation of, okay, rich one atom, one element rich intermetallics. Okay, is it clear about the anti-sites? Any doubts? Okay, then another thing, second one, okay, triple defects. Okay, triple defects. If I take nickel aluminum, okay, nickel aluminum, okay, we know that in a, okay, if I take, okay, this is nickel aluminum is a B2 BCC derivative, B2 compound BCC derivative. Okay, so it should have a corner atom should be, okay, one type of atoms can be nickel or aluminum. Its body centered will be another atom. In this case, we can consider corner atoms is nickel and body centered atom is a aluminum. So when do you say that there is a triple defect exist? Okay, look at here. One, okay, two corner atoms, okay, are being missed. Okay, and we are having, instead of a aluminum, we'll be having a, okay, nickel. So there is an anti-site plus vacancy. Okay, so formation of a vacancies plus anti-site, okay, together is called triple defect. Okay, so the effective number of atoms still, okay, we are going to have, okay, NiL, nickel aluminum, okay. But what happened, we are having a one anti-site defect together with a two vacancies. Okay, corner atoms. So this is called triple defect. Okay, So if we have this kind of defects, okay, it can accommodate, okay, more of one kind of, okay, element. So we can get a aluminum rich or a nickel rich can be formed very easily in this kind of structure. Even if there is a B2 type of structure, there is a high tendency for formation of, okay, solid solution intermetallics. This is simply called some solid solution alloy intermetallics can form. That means aluminum rich or nickel rich compounds can form. Okay, is it clear about the anti-sites and triple defects?
Sir, so basically we are saying because of these defects, we are able to form, complex compounds or any alloys which generally we are using for turbine blades and all those things.
Turbine blades is, yes, slightly different. We'll come to that. Just I'm talking about individual intermetallics. So far, I'm talking about individual intermetallics.
Like sir, just example CMS-X4 alloy, basically it is the same thing, Ni3Al based alloy only, but it is having 12, alloying element. So of course they need to go somewhere, they'll be going in these anti-sites and triple defects only. So until unless the defects are there, the alloy design may not be possible. Am I right?
No, actually here, okay, I'm talking about if I take, okay, individual nickel aluminide, okay, if I take individual
Not
nickel
the
aluminide,
alloy person.
no,
Okay,
no,
sir.
nickel aluminide, okay, I said we have a, okay, in phase diagram, we have a some, okay, wide range of some stability, okay, of the compound. We do have a, supposed to 50 atom percent, 50 atom percent of nickel and aluminum, am I right? If we take NaAl, but we do see some 44%, okay, nickel and, okay, 54% nickel will be there, okay. Some there is a some 10%, okay, wide variation is there, okay, in the composition. So
Okay,
those
got
can
it, got it.
come, okay, because of this defect formation. Okay, by having some non-equilibrium conditions, we can generate these defects that can lead to formation of, okay, wide, okay, range of composition. Okay. According to Ni, if I say NiAl, okay, it should be Ni, okay, 50 atom percent of nickel and aluminum 50 atom percent. But it's not necessary to be, okay. We can also see, okay, nickel rich or aluminum rich compound. But still, we call it as a nickel aluminate because, okay, formation of these defects, which can accommodate aluminum rich or, okay, nickel rich kind of compound. Okay, it's a single intermetallic I'm talking about. Okay? So far, I'm not talking about anything about superalloy. Superalloys will contain nickel aluminides. Okay, nickel is a matrix. Okay, so there is nickel is a matrix, or like iron is a matrix, or cobalt is a matrix in a superalloys. There we do see formation of these intermetallics. Okay, but we do see some. There are some, okay, titanium aluminides people are using. Okay, some of the space applications directly as an intermetallic. Okay, not as a, okay, form of a presence of intermetallic in a matrix. Here I'm just talking about only as a intermetallic. If it is a single intermetallic, how it can, okay, what type of defects are going to form in intermetallics. Clear?
Yes, sir.
Yeah, these are two popular, okay, these are close to vacancy type of defects, okay, interstitial and vacancy. What we see in metals, we do see vacancy defects and solid, okay, interstitial solids, okay, defects. So similar to that, okay, we do see here anti-sets and triple defects. Apart from this, okay, there are other type of defects what we see, okay. So these are point defects. This is common category of point defects. We also see, okay, surface defects. Okay, we also see line defects in the material. Okay, so line defects. Okay, for example, what is the dislocations are the line defects in metals. Similarly, here also we do see, okay, defects like dislocations. So that is a kind of, okay, as compared to ceramics, okay, intermetallics behave, okay, between, okay, metals and ceramics. Some of the properties, okay, in, okay, will be having close to metals. Some of the properties are close to ceramics. Okay, so that's a kind of, okay, significance of intermetallics. Okay, these are neither metals nor ceramics, but can have a combined action of metals properties and the ceramics. So that's why intermetallics have come, okay, become a little bit popular. Okay, because these can exhibit some ductility as compared to ceramics. Okay, at the same time, intermetallics can have high melting points, like close to metals because of compound formation. Okay, so these intermetals can also have a defects like, okay, point defects. Under point defects, anti-sites and triple defects come. Okay, under line defects, dislocations are going to present. Okay, here because of this structure we call, okay, those defects are like a super, the lattice what you are talking about now, okay, it's a super lattice. This is a super lattice, it's not a single lattice, okay. Super lattice, why you are saying two different type of atoms are present, that's why it's called super lattice. Similarly, okay, dislocation we call super dislocations, okay, super partials, okay. In metal simply say dislocation, perfect dislocation and partials, Shockley, okay, frank partials kind of thing. In intermetallics we do say super dislocation and super partials, okay. Terminology is used for a line defects, okay. Similarly to similar to line defects we also see surface defects, okay, like boundaries, okay. These are called anti-phase boundary, okay, superlattice intrinsic stacking faults, complex stacking faults, and superlattice extrinsic stacking faults. Okay, these are common, okay, 2D, okay, defects, surface defects. Antiphase boundaries can form, okay. Superlattice, okay, because we are talking about the superlattice intrinsic stacking fault, complex stacking faults, superlattice extrinsic stacking faults are also going to form in intermetallics. What is meaning of antiphase boundary? Any idea antiphase boundary?
Sir, it is the change in the ordering of these atoms. Like if there is aluminum, copper in the whole series, so there are chances that aluminum, copper, aluminum will form. So that extra, the boundary at which there will be a difference in the uh, ordering of these atoms is called the antiphase boundary.
Yeah, you are very close to it, okay. So if I take a NiAl compound, NiAl, okay, B2 compound, okay. So typically, okay, across a boundary, typically we'll have a opposite type of atoms, okay. If I take, okay, Ni between a the bonding will be between, okay, nickel and aluminum, typically supposed to be, okay. Then it is a perfect, okay. But, okay, there will be boundaries, okay, which can form during deformation, okay, or, okay, typical motion during deformation can form, okay, during cooling also some type of bond is formed, where we are going to see, okay, okay, bonding between similar atoms, okay, between nickel nickel, between aluminum aluminum, okay. So that is called antiphase boundary, okay. So typically if I take, okay, atomic arrangement, okay, at a particular plane, okay, if you take a particular across a, okay, plane x, okay, xx plane. So typically across this boundary we are going to have a, okay, unlike bonding between unlike atoms. However, because of some activity, okay, shear activity or something, somehow it's short shifted, okay. So that can lead to bonding between, okay, similar atoms, okay. So this is called formation of a antiphase boundary, okay. When, okay, this kind of bonding happens between nickel and aluminum, the bonding will be different. Between self met atoms, between nickel and aluminum, the atom, okay, atomic bond is different. So that can lead to change in energy, okay. That energy called antiphase boundary energy, okay. So that means whenever there's antiphase boundary forms, okay, locally the energy is going to be different, okay. So that type of AA bonds, BB bonds, okay, we are considering AB type of compound. So the bonding between AA and BB is different than bonding between AB. So that can lead to, that can result in, okay, formation of a antiphase boundary. That boundary is called antiphase boundary, and it has certain energy. Also associated with a certain energy is called antiphase boundary energy. Okay. So similarly, okay, typically when there is dislocation moves, okay, so that can create, okay, one moment of partial, one dislocation movement can lead to a formation of these antiphase boundaries. The next partial comes, we can close it, okay. That means again we can come back to a regular arrangement, okay. So the moment of, okay, dislocations can also lead to formation of a antiphase boundaries in intermetallics. So we also see, okay, stacking faults. Okay, intermetallics can also have some stacking faults. It can be a, okay, intrinsic stacking faults, like what we say. Okay, we heard, okay, intrinsic stacking faults, extrinsic stacking faults will also present in intermetallics. Apart from this intrinsic stacking faults, we also see complex stacking faults also going to form. So this is basically comes from a dislocation arrangement. Okay, stacking faults basically sequence can be disturbed. The sequence of atoms can be disturbed. Okay, when there is a dislocation moment in the crystal. Okay, so typically if I take okay L12 structure A3B okay Ni3Al kind of compound. Okay, if I arrange and take a okay projection on a plane, if I take a projection on a plane one plane. Okay, because of some dislocation activity or deformation shearing activity, the atoms can slide, okay, can move in different movement directions. If okay, atoms move in this direction, okay, across this plane, that can lead to formation of antiphase bond. If atoms move in this sequence, in this direction or in this direction, we do see different type of stacking faults. The type of stacking fault is going to be different because the type of atoms present are different. Okay, so that can lead to a different type of stacking faults. The stacking faults can be SAF, SASF, or SCSF, or CSF. Okay, so these are different types of stacking faults we do see because of a different type of atoms, not a single same type of atoms. In metals, we do see same type of metal atoms. But here we are talking about two different metal atoms are going to present, and the number of atoms are going to be different. Okay, that can lead to formation of okay stacking faults like a complex stacking faults or okay SISF or SCSF. Anti-phase bond is very clear because there is a okay here opposite boundaries. So suppose opposite atoms bonding will be there, but once there is a boundary forms, okay, that can lead to formation of same type of bonds. That's the anti-phase bond. So coming to stacking faults, okay, what is the difference between complex stacking fault and okay intrinsic or extrinsic stacking faults? Okay, so this basically come okay. For example, if I take okay intermetallics, okay, if it is a FCC derivative, okay, we know for FCC, okay, what is the okay dislocation, perfect dislocation? What is the perfect dislocation for FCC? If you take a FCC metal nickel, if you take a
Half
nickel,
1 1.
one okay A by 2 110. Am I right? Okay, the Burgers vector is going to be A by 2 110. If it is a metal, in case of metal intermetallics, we call the super lattice. It's not a simple lattice, it's a super lattice. That's why actually we do not have A by 2, only your super okay dislocation is basically 110. Okay. So this 110 okay can decompose okay energetically, can decompose energetically okay in this fashion, or can also decompose in this way, can also decompose in this way. Okay, the decomposition can be all are actually energetically feasible if you do the simple okay your energy okay way of doing this thing. Frank rule, by applying Frank rule, we'll come to know. So this super lattice dislocation okay can decompose into like this, or can also decompose into like this, can also decompose into like this. If it okay, for example, this decompose into like this one by 2 110, okay, that means it's like a perfect dislocation in a metal. Okay, your okay super dislocation becoming a perfect dislocation here. Okay, so then between them we are going to see formation of an antiphase bond if it decompose like this. If it decompose like this, okay, A by 3 1 1 1 2, okay, like this, that the okay, between we are going to create a fault. Okay, it's called intrinsic superlattice intrinsic stacking fault. Okay. We may also see okay, formation of okay decomposition of this 110 can decompose into in this way. Okay, so if it between these two okay partials, okay, we are going to say complex stacking fault. Okay, between these two we are going to have complex stacking fault. Okay, again between these partials we are going to say antiphase bond. Okay, so the way okay the particular dislocation is going to decompose, okay, that can lead to formation of complex stacking faults, antiphase boundaries, and okay intrinsic stacking fault or extrinsic stacking fault. So if you look at here, okay, I think we already discussed antiphase boundary is basically disturbance of unlike nearest neighbors in the plane and are relatively high energy faults. Similarly, superlattice intrinsic stacking fault is basically, it means, what does it mean? There's no nearest neighbor violations, but stacking sequence is going to change, but nearest neighbors are going to be not violated. We are going to have almost same type of nearest neighbors. Okay. Similarly, in superlattice sections also we are going to have, okay, only first nearest neighbors are not going to get violated, but after that we may see some violations. Okay. Next neighbor atoms are going to get violated. Okay. So in case of complex stacking faults, okay, it is like a stacking faults what we see in FCC structure. So these are actually going to be, okay, very high energy. Okay. Complex stacking faults are going to have high energy as compared to other, okay, defects what we see in intermetallics. Okay. Is it clear about this different types of stacking faults and, okay, 2D defects what we see in intermetallics? Surface defects, okay? Any doubts here? Are there any doubts?
Sir, the anti-phase boundary can't be considered as a stacking fault, right?
No, they do not call it, it's just, okay, it's a boundary. Okay, the atomic arrangement has been locally changed. So this is also fault. Okay, it's also fault, but it's not really a, like a stacking fault. Okay, they have given a like an anti-phase boundary instead of calling say stacking fault. It's also fault. It's a defect, but not necessarily stacking fault kind of.
Is it because the arrangement is not changing
Arrangement is,
after after the movement?
arrangement is going to change. Once you have the anti-phase boundary means actually it is going to be created. Okay, arrangement local. Okay, at the boundary we do see local arrangement is going to be get stuck. Okay, but they do not call here in the, they do not call it a stacking fault. But it's also basically we are going to see, okay, stacking fault is going to change. The sequence of stacking, okay, atom stacking is going to change. It is close to stacking fault, okay, a defect disturbing the stacking sequence. But they coined it as a anti-phase boundary. We do see change, okay, the stacking sequence is going to change across the boundary. Okay.
Yes, sir. Understood.
So complex stacking faults, if they form, those are actually highest energy state. Okay, we are going to have a high energy. Okay, provides high energy as compared to other, okay, defects what we see. Okay, complex stacking fault energy is greater than anti-phase boundary. Anti-phase boundaries energy is greater than, okay, SISF and CASF. Okay, the same superlattice can decompose in different ways, so that can lead to formation of this type of defects. Okay, so this is actually about the defects what we see in intermetallics. So the next one, okay, deformation behavior. Okay, we talk about deformation behavior of intermetallics. We are talking about plastic deformation. Okay, so I think we have seen, okay, I think in one earlier lectures, okay, I think during, I think third or fourth lecture we have seen, okay, CRS critical reservoir shear stress, okay, as a function of temperature, or yield stress. If you take yield stress of material, how it changes as a function of temperature. Okay, FCC materials is like less sensitive to temperature change. Okay, whereas BCC, if you go to, okay, lower and lower temperature, the stress required, a critical resource is required for plastic form is going to increase, okay, with decreasing temperature. Okay. If you take intermetallics, okay, like a B2, L1 to L2, okay, we do see, okay, okay, initially, okay, the stress may be constant, the critical resource is required for plastic formation may be constant, but with some temperature it is going to increase. It's called anomaly. Okay, plastic deformation, okay, anomaly what we see in intermetallics. Okay, instead of decreasing, typically we know that, okay, with increasing temperature, typically thermal activation is going to lead, okay, can happen. That usually brings down the stress requirement. However, okay, instead of like that, what we are seeing in intermetallics, okay, rather than decreasing, it's going to increase. The stress requirement is going to increase up to certain temperature. Then it's going to follow the regular trend. Okay, so this has been shown, okay, experimentally in various intermetallics. Okay, Ni3L, okay, Ni3 silicide, nickel, okay, nickel silicide, nickel germaniates. So people have shown, okay, increase in, okay, stress, yield stress of a material, okay, with increasing temperature. If you deform only this particular intermetallics directly, okay, we do see the stress requirement is going to increase with increasing temperature. After beyond certain temperature, it decreases. Okay, so this is called anomaly behavior. Okay, plasticity anomaly. Okay, what we see in intermetallics. Okay, this has been observed not only in tension, can also be seen in compression, both tension and compression. We do see this increasing yield stress with temperature. Okay. Is it clear what I'm talking about? Deformation behavior of intermetallics.
So in the
Now, because
top left corner, this third graph where alpha and beta is given, what is this alpha basically? B in is seen as
beryllium spinel, different some other compounds. Okay, some other spinel type of compounds. If we have, okay, is going to decrease initially, then again increases stress. In case of okay B2, your intermetallics, typical intermetallics, what we see is typically follow like this.
I mean, beryllium as such shows this phenomena. That's what you're saying.
Yeah, this also is going initially is going to decrease. Okay,
Uh-huh.
after certain temperature, again starting the stress is going to increase. The stress critical, okay,
Okay.
yield strength of material is going to increase. Some ceramics, okay, spinels, okay, some ceramics will have spinel structures. Those also show increase in yield stress with increasing temperature. Any doubts here? So why? Okay, why? Okay, because see now, for example, in superalloys, okay, when you add aluminum, titanium to nickel, okay, so by adding some amount of aluminum, nickel, so aluminum to nickel or titanium to nickel, we can expect formation of these intermetallics. Okay, so when the quantity is small, we do expect Na3L formation rather than a NaAl. Okay, so if the aluminum quantity is more, then we can see more NaL is going to form. Okay, so at a small quantity, typical superalloys contains some amount, okay, some around 4 to 5% aluminum or titanium is added. Okay, so the purpose is basically to form this, okay, Ni3L compound in superalloys. Okay, nickel matrix plus, okay, the nickel matrix typically called gamma matrix, and this Na3L is called gamma prime. Okay, L12 structure. Okay, gamma prime precipitates. Okay, gamma prime precipitates typically we can have between anywhere between 40 to 70%. Precipitate quantity will be more than your matrix also can be seen in superalloys. Okay, the purpose of this, okay, the advantage of having this Na3L is basically, okay, to retain, okay, high temperatures, okay, strength at high temperatures. Because if we take only nickel, okay, typically, okay, the strength usually decreases because of thermal activation, because of climb, cross slip activity, which can take place. Thermal activation can happen very easily at high temperature. The strength decreases, the creep resistance is going to come down. However, if nickel aluminide is present, Na3 is present in a matrix, okay, one, we are going to have precipitation hardening. Okay, at the same time, the nickel aluminide itself, okay, behaves differently than the nickel matrix. Okay, so with the temperature, with increasing temperature, strength of the nickel aluminide is going to increase. That means either you can, okay, retain high strength of the nickel matrix, or still you can increase the strength of a metal. Most of the times, the strength is not going. Whatever strength of nickel matrix coming down, that is being compensated with the rise in stress requirement for nickel aluminide deformation. Okay, as a result, we do see there is a stability of strength. Okay, thermal stability of strength we are going to see in a superalloys up to certain temperature, typically, okay, up to 600, 700 degrees Celsius. After that, we do see the strength is going to come down. Okay, so that's the kind of, okay, purpose of that, its importance, whatever you can say. Okay, superalloys, okay, are going to retain, okay, high temperature, the strength at high temperature, because of presence of these, okay, intermetallics like Na3L, where which these compounds are going to exhibit plastic anomaly, okay, that can lead to retaining the strength at high temperature. Okay, is it clear? I hope I'm online. Am I online?
Yes, sir.
Yes.
Okay, so now,
Sir,
okay,
the strength is only there at a particular temperature window, right? That high strength
yes,
will get retained only for that peak that can be
yes.
seen.
After that is going to decrease. Okay,
Okay. So we need to make sure that the application where we want this high strength is only going towards that temperature range, that small.
Yes, yes. That's a super alloys, okay? You can use very safely up to 700, 750 degrees Celsius. After that, okay, your strength drops down drastically. Okay, that's the creep resistance is also going to come down. Okay, so depending how much nickel aluminate content is there, accordingly we can raise that bar to 800 people also up to 900. The creep resistance of sopralus is good. Beyond that, we do see very low creep resistance. Okay, most of the times, okay,
Sir, on
most
the graph,
applications.
it is showing till only 400 degrees, sir. Like
No,
I
no,
can see on the graph.
this is 600 degrees Celsius. This is
Okay, okay, okay. I was
600
seeing the
degrees.
other one. Okay.
600 degrees Celsius. Even if we take this one, okay, so even if you go to 800, still your strength is actually higher than, okay, what you can see for the nickel matrix. Okay, still, okay, that basically compensates even as up to, people have seen up to, the creep resistance is good up to 859 degrees Celsius. The best one comes around this peak temperature 600, 700 degrees Celsius. The best creep resistance comes. Okay, by just changing volume fraction of nickel aluminide, we can, okay, extend the, okay, temperature limit slightly. Okay, so 900 is the maximum temperature we can use superalloys. Okay, if we have a nickel aluminide in a nickel matrix, so people are trying to add other things so that we can still, whether you can okay, extend this temperature. Okay, there's a lot of research going on in superalloys to have a better and better. Okay, we know single crystals are good, no doubt in that, for creep resistance. Okay, single crystal itself is not sufficient. Okay, the strength is very low for single crystals. There are no boundaries. The creep resistance is supposed to be high, but the strength of the nickel, the matrix itself is a low. So by adding this precipitates all this, you can retain the high strength. Okay, you can have a high strength of single crystal, but we can have stability wise, thermal stability wise, we can improve it by having a higher volume fraction of this. Okay, intermetallics in the material. Okay, so why? Okay, why this intermetallics exhibit this plastic anisotropy? Any idea?
Sir, I don't know fully, but I had read somewhere that these locations cross slip, and after cross slipping, they split into partials. So
Hmm.
this location gets locked and this strength is increased.
Okay. Yeah, I think here, I think, yeah, what you read is actually almost right. Okay. It is something to do with, okay, barriers, okay, which will form. Okay. We have studied, okay, in metals, okay, we do see formation of some barriers, lomer quartal barriers, okay, lomer barriers are going to form. So like that, okay, intermetallics, when there is a plastic deformation, okay, the slip activity is going to take place. Okay, this, okay, in this intermetallics, okay, we do see some additional barriers are going to be created. Okay, so that is called, okay, some lock. Okay, Lomer Carter locks. Okay, like that. Okay, we do see in intermetallics. So this has been explained by two people. Okay, Kier and Wilsdorf. Okay, Kier, Wilsdorf. Okay, so what they said, okay, it is going to, during plastic deformation of intermetallic like Ni3L or NaL. Okay, what happens? Okay, formation of, okay, this, see, for example, if there is a super partial like this, it is decomposing, okay, into, okay, different partials. Okay, different partials along with the formation of some defects. Okay, so if I take here, okay, we do have, okay, two partials here separated with some antiphase boundary and two partials here. So where in the plane 111 plane, because 110 is the direction, 111 is the plane for a FCC. Okay, since a L12 is a okay, L12 is a FCC derivative, so the closed packed, okay, direction is 110 and plane is 111. So on 11 plane, okay, this reaction is going to take place. However, okay, with further deformation or with the temperature, whatever you see with the temperature typically, okay, with the temperature, there is a cross slip activity is going to activate it. Okay, this cross slip activity, because of cross slip activity, what happens? These partials, whatever forms, okay, these two partials can react, okay, together, can form a, okay, a dislocation, okay, which can cross slip onto a 100 plane. Initially, this deformation activity happening in 111 plane. So, however, these two partials can react, okay, and can get cross slip. These two can cross slip into a 100 plane. Okay, after certain amount of deformation at time temperature, again what happens, whatever the dislocation reaction formed, that can decompose again into a parallel one plane. Okay, parallel one plane, it can again decompose. So this lead to a formation of a lock. Okay, so anything that we are similar to what you have seen lower quarter lock. Okay, here also what we see in intermetallics. Okay, some of the particles are going to react. Okay, can form a perfect dislocation. Okay, dislocation can form, and that dislocation again decomposing. Okay, after certain amount of it can decompose into another plane. So that leads to difficulty of a cross again. Okay, when it forms in 100, now it's like a so like act as a barrier again further. Okay, so after certain amount of formation, again it can decompose and form another plane. Now, activity is happening in another one plane. So the whole thing, is called formation of a Kier-Wilsdorf lock. Okay, so this kind of locks, will act as a barriers for further dislocation motion. Further dislocation motion. Okay, so this usually happens once you apply some thermal energy. Okay, this cross slip activity happens easily. Okay, so because of temperature, so we do see cross slip activity, then that basically controls the further deformation of a material. So that can lead to a increased strength rather than decreasing strength with temperature. The same thing has been explained in a better manner from some another textbook I have taken. Okay, it's the same. Okay, almost it's the same. Okay, we have a one plane. Okay, so the dislocation is going to decompose into partials. Okay, and have a antiphase boundary. So these 2, 3, and 4 partials are going to slide cross slip onto a 001 plane. Okay, so this creates a antiphase boundary. Okay, after that again what we see, this can decompose into 3 and 4 on a parallel 1 plane. Okay, so this thing can lead to a formation of a this kind of look at here. Initially, if you talk at room temperature, we do see very nice slip lines and like this. Okay, dislocation arrangement will be in the kind of like this lines. However, with temperature, okay, we do see formation of these locks. Okay. This kind of these locks are going to be formed. So these locks basically controls further plastic deformation. So as a result, the strength of a material is going to increase. Okay, so this mechanism called Kier-Wilsdorf mechanism, which has been well established and shown experimentally the formation of these locks with temperature in intermetallic compounds. Okay, is it clear?
Hello, sir. So this
Yes.
decomposition of logs, why does this only happen here in the case of intermetallics?
Decomposition is energetic because we have superlattice. When you apply a shear stress, dislocation is going to move. Basically, that's called slip activity. So this dislocation can actually decompose. Okay, energetically can decompose into a partials. Okay, if similar to metals, okay, we do see formation of a partials. Okay, here we do see superpartials. Initially, we say superpartials, and those superpartials can decompose into Shockley partials. It's
So,
an energetically feasible reactions, okay, which can form, okay, in a particular slip plane. Okay, we can see formation of this.
so this
So we are,
decomposition does form in the case of metals also, right?
yes, yes, yes.
So over there it doesn't impart more strength.
No, it's what happens is the cross slip happens immediately. Okay, so that is kind of easy thing that will not form easy barriers at high temperature. Lower quarter locks can happen room temperature, but at high temperature those locks will not happen. Okay? At low temperature only, room temperature, low temperature only, the locks are going to be very effective in metals. But here, these locks are going to form at high temperatures. Okay.
Okay, sir.
because we need for cross slip to happen, okay, we need to apply some temperature, okay, some thermal activation required. So that, but actually during that process, it is going to create some locks. Okay. This kind of loops, okay, dislocation loops are going to form, okay. So for that, dislocation motion is going to be hindered. Once you hinder the dislocation motion, that basically we need to have higher and higher stress for further deformation to take place. That indicates the strength of material is increasing with temperature. Okay. So in this fashion, when it decomposes and cross slips, we are creating more, okay, defects in the material. Okay. So anti-phase boundaries are forming here and here. Okay. So this basically further increase your strength requirement, stress requirement for the deformation. You are creating faults, at the same time you are creating a, okay, kind of locks within a dislocation structure. So formation of these faults and, okay, stacking faults, anti-phase boundaries, along with we are also, okay, saying, okay, formation of these locks, additional locks, that lead to higher stress requirement for further deformation to take place. Okay, is it clear? I think it's a very nice way of, okay, explaining about the Kier-Wilsdorf law formation. Okay. So I think this is about, okay, deformation behavior of intermetallics. Typically, okay, I've taken only example of L12, which is, okay, significance as per supervisor concern. So this kind of thing, okay, anomaly has been seen not only Ni3L, okay, has been also seen other intermetallics. Of course, some other NiL also, okay, people have observed formation of this, okay, increasing stress requirement with increasing temperature. Okay. So the other important thing, okay, these intermetal is going to have a higher temperature melting points relatively, okay, as compared to if you take Na3L, okay, NaL, sorry, if you take NaL, okay, nickel and aluminum melting points, we know, okay, 1400 around 1470 degrees Celsius, other one is, okay, 660 degrees Celsius, but NaL will be having higher intermetal comment relatively. Okay. At the same time, density. Okay. Nickel has a high density, aluminum has a low density, NiL has a relatively low density. Okay. These are like a low density intermetallic. Okay, you'll have a low density, at the same time higher temperature, melting temperature. That means actually your creep resistance is high. We have a high melting point means, okay. Okay, at the same time, this is a low density compound. So that way I think, so people actually trying to use titanium aluminides so that, okay, you can reduce the density of the overall structure. So somebody is having doubt, something.
Sir, in the formation of this KW log, the schematic, does it shows that the two superpartial will combine at point A, then again split and again combine at B? Is it so?
Yes, yes. These two combine, 3 and 4 combine together and can cross slip into a, okay, 001 plane.
Or
After,
again, they
okay,
have,
again,
like in
they
right
again they
side image,
decompose
right side image, sir. It is
here.
visible here also. That at point
Mhm.
A and B, they combine and then further
Yes.
split, right?
Yes.
But we are saying that this
Again
whole,
split.
yeah,
Again
we are
splitting,
saying
okay,
this
here.
process, I mean, A to B, this is a stable process, right? That's how this lock will be there. It retains.
Yes, those are going to be retained, okay. Because boundaries are creating, additional boundaries are being created, okay, in different planes, okay. Additional boundaries are being created. So that way basically your energy is now, okay, there. High anti-phase boundary forms means energy you are creating there, additional energy there.
And so this in the schematic, this some curvature is shown. Is it like the way actual also is being witnessed, or just for
Just it's a
representation?
schematic based on, I think this, you may see like this, okay, some kind of curvature people have observed. That's why this.
Okay.
Okay. So one of the drawbacks of this intermetallic, so the advantage we have discussed, okay, the strength is going to increase with the temperature up to certain temperature. That means creep resistance will be very good, and we can have a low density typically, okay, as compared to, okay, one of the parent atoms. Okay. and okay, high melting points, typically higher melting points will be seen. Those are the kind of advantages what we see. But one of the major drawbacks, okay, of the intermetallics is the low ductility. Okay? When it comes to ductility or strength, okay, so strength is actually very high, comparable. You may see some of the ceramics. Okay, fracture strength basically is higher than ceramics. However, okay, the ductility is low. Okay, most of the intermetallics, if I take only just if I deform only Ni3Al, okay, or if I take a superalloy which is having high, so the ductility is very low. Okay, typically 4 to 5%, less than 6% ductility will be seen in the intermetallic compounds. Yeah, so people are trying to improve the ductility, okay, by putting some, by doping something else, in the intermetallics. So one of the things actually, for example, Ni3L typically will have a 4 to 5% ductility. Okay. So if I want to improve the ductility, what people are trying by adding some boron, small amount of less than 100 ppm of boron, to the okay to the intermetallic compound while preparing, while processing, while synthesizing compound. That time we add boron. Even supralose also, people add some amount of boron. That basically the purpose of boron is basically to improve the ductility of intermetallic compound. Okay, so typically, we have across the boundaries. Typically, we do see the presence of same type of bonds instead of unlike between atoms. Okay, so if there is a bonding between A B, then it's okay because we are having height. Okay. But we do see the formation of the bonds across the boundaries between similar atoms. So that lead to a lower strength regions. Okay, so there the crack can propagate very easily. Okay, crack can very easily propagate along this thing. So that is a problem. So what people are trying to see by adding boron, it basically controls the bonding across the boundaries. That's one thing. Okay, one kind of method people are using. Okay, by addition of some kind of another atom, which can segregate to the boundaries, that can control the bonding across the boundary. So that actually people have shown, in case of by addition of small amount of boron, with increasing boron content, with increasing boron content, so we do see, increase in tensile elongation. Okay. People have demonstrated, up to certain amount of, boron, we can have a improved, tensile elongation in, Na3L compound. So this kind of thing, so people are actually, this is one of the challenges of the intermetallics. Where the problem is there, because if you want to form a component, I need to have a high ductility. If you want to form by rod form, in a rod form, so ductility is one of the major concerns. So people are actually trying to see the methods to improve the ductility intermetallics. Okay, any doubts?
Sir, can you repeat the this thing when you said that at this grain boundary the cracks formation easy? I could not get that.
Yeah, usually, if there is a crack, propagating crack, is not easy. Okay, when there is a bonding between unlike atoms, because if bonding between Ni and Al is stronger than between nickel and between aluminum. Okay, if there is a reaction happening between two different atoms, that is a chemical bond is happening. Okay, in case of nickel bonding, aluminum bonding, it's a metallic bond. Okay, so whenever at the boundaries, what people have observed, most of the bonds across the boundary are between similar atoms. The bonding happening between the similar atoms. Those are the weakest points for the crack to propagate very easily. Okay, if we can control formation of bonding between similar atoms, that may improve the ductility of intermetallic compound. Okay, that means you have to control the arrest the crack propagation. Okay, so that actually people have shown that by adding some dopants like hafnium, boron, some elements, people have shown that can actually minimize the bonding of formation of bonds between similar atoms at the grain boundaries. Okay, that is one way of explain. But there is so far there is no clear understanding how boron addition can improve the ductility of a Na3Al. It is a kind of speculation. People have thought the boron is going to segregate very easily. It's being a small in atom size, is going to segregate the boundaries. Okay, so segregation of boron led to improved ductility. So people are actually suspected that there is a possibility of avoiding this formation of a bonds between similar atoms.
So that I got the point, sir. But in that case, does this mean? I mean, in general, can we say in general at the grain boundary, like as we say A and BB type of bonds are there for other metals also? Can we say so or no?
Other metals means no.
Like any maybe titanium alloy or some other thing. Can I say this is one of the feature of grain boundary that similar bonds between similar atoms maybe chances are more at grain boundary.
Yes, yes, yeah. It has been shown. Okay, at many places. Okay, the boundaries will be having bonding between similar atoms rather than dissimilar atoms.
Okay, sir. Got it.
People have considered those might be weakest points for the crack to propagate.
Because not only the grain boundary, one of my work also we have seen the precipitate and eutectic boundary. I mean that's what we have. The crack, propagate through that boundary also. That also acts as a boundary.
Yeah, eutectic compounds are actually very dangerous. Okay,
Sir.
so because those are like a softest, low melting point constituents. Okay, that can lead to easy formation. So eutectic points always a problem. Eutectic compounds. It's a kind of
Hello, sir.
explanation was given, but there's no clear cut understanding. No, still people are working on what is the role of boron on improving ductility of Ni3L compound. But this same boron, if we add it nickel aluminum, it's not effective. It is effective only, it was observed only effective in only improving the ductility of Ni3L, not in nickel aluminate. That's why the people have started whatever people have hypothesized it's not valid in all the intermetallic compounds. So that's still the research is alive. Yes, somebody has doubt.
Yes, sir. I was saying that in this case, then having no bonds is better than having a weak bond. You're saying, like,
Yeah.
when boron breaks the bond. So, sir, in that case, when there is no bond, can't the crack propagate just like that? I mean, there is no bond, right? It's an empty space.
Mm-hmm.
So, can't the crack propagate? And
no, that's what nobody knows what is actually. People have seen boron segregating, but actually after that, how it is it may form some compounds again. The borides are going to form. Okay, because not only boron, if you take a superalloys, if you add boron is segregating. Along with boron, we do see some additional segregation, chromium, tungsten, those are going to get segregated to the boundaries. So those will form an intermetallic compound with a boron. Okay, so that actually people are talking about. Okay, now actually that boron is segregating, but at the same time that boron is forming some borides, some borides. Okay, so those borides are basically increasing the crack propagation resistance.
okay, sir, understood.
Yes. So only within just nickel aluminate, people have shown improvement of boron addition. Okay, even superalloys also. Okay, gamma plus gamma prime, nickel and Ni3L. Okay, there also people have observed addition of boron leading to increased ductility, tensile ductility. So the role is still not clear. So I think recently, I think even one of our students working with Pant and myself, we have one student. So there also we have shown how this boron, role of boron, how it is forming. Okay, one of the things what we have shown, formation of what type of boride is forming. There are different types of borides formed. So one type of boride, leading to a improved ductility. So it's like still, that's what I'm saying. The research is still alive, on the role of boron. Any more doubts? Yes. there are no doubts. I think this is a basically end to the intermetallics. Okay, what we discussed. Okay, in today's lecture. So with that, okay, this is a course content. I tried my best to cover most of the content. I think I left the stress relaxation. Okay, these details. So I think rest of the things I tried as much as possible, okay, related to plastic deformation plus microstructure evaluation. Okay, but if we talk about plastic deformation, it's a huge subject. It is a ocean. So I think picked up one small, okay, lane, okay, small path related to the deformation, which leading to a microstructure evolution. Okay. So I think whatever we discussed is actually in this course, it is related to plastic formation plus microstructure evolution. I hope something has gone into your mind from this by taking this course. Okay. So if there are any, I think anything else you want to say, just speak up. So
Yes, sir. Just personally want to thank you. I think you spend the right amount of time in putting time onto conceptual understanding of these topics. So I personally enjoyed this course. So
thank you. Yeah.
thank you for all your effort.
Thank you very much. Yeah. So,
This course has been very useful to me because like clearing this big understanding. So when I go to the research part, like when I read about these research topics, so I don't need to go to the basics, and I can easily correlate between the two topics that you teach, and I will be able to give more time in critically analyzing that paper rather than like studying the basics of that thing.
okay.
So I have studied like I've done a little bit of like a literature review for my seminar and my research. So I found this course very much useful because all this dynamic strain aging, crystallographic shear, the basics of these topics were very much useful in understanding how this dynamic, how my in my research, how different kind of topics interplay and what are the gaps in the literature. Everything.
Okay.
So I find this subject very much useful in terms of research, and it was very good. Thank you.
Okay. I'm good to know about it. So
Sir, actually, that course you are taking, it's actually, sir, we
hmm,
are enjoying a lot. Actually, sir, the thing you are putting more effort. Actually, for every classes, you are putting more effort to to give a good thing to us, sir. So it's and also you didn't actually, sir. Last 3 semester we have your classes, but last 3 semester we didn't see any you missed the classes. So almost every classes. So almost every classes are actually in last 2 semesters you didn't miss even a single class. But that way of your commitment actually, sir, we don't know how to tell. So actually that's a great thing, sir. And also that course content what you are teach in taught in that last semester, actually last year, compared to this year, you are giving a lot of new insights. So you are not taking that same thing whatever you are taught in that last semester, you are not taking that same thing to this semester. This semester you are adding more and things. So actually, sir, I gone through that last semester ppt also. I think you are added more than 20%. That if you are taking that last semester as well as this semester, you are adding more than 20% of things they are new based on your research and all these things, all these your studies you are adding every year, sir. So it's a great thing to us because you are adding every year. So we are studying a new things compared to a last year student. We are studying some new things. And also, sir, one thing, you always start from basics, sir. So this is a most actually, sir, a good thing from you we are telling, because if some students are not from metallurgical background, you also consider that student also. So you always start from the basics. So actually, sir, this is a very good thing. So everyone in the class, so if 40 students are in the class, every 40 students have to understand from the base. So it's a very good thing, sir, for us. So actually, sir, we don't have any words to say, sir, your class is super like that. Sir, you are always super, sir. So we don't know how to tell. So this is a good course, sir. We are taking from start from that lecture number 1 to lecture number 24. every day you are putting more effort compared to us. We are only listening our lectures, but you are studying more things compared to us. You are studying more and more. You are putting so much effort to the presentations, and you are giving these things to us, sir. So to tell, you are we are feeling very proud to get a professor like you, sir. So thank you so much. So actually, sir, the God will give good like uh, good things to you. So you will continue this year on year. So many students from that student community will get benefits.
Yeah, thank you very much for your kind words. I think, yeah. So I'm speechless now, I think. So yeah, actually you're right. Actually, I changed my slide where the way putting the information. I'm adding some of the things slowly one after the other. So I'm
Actually, the
refining my slides
same
also.
thing that I want to do, because I also have requested you to attend these classes last year also. But somehow timing was not so suitable, because I'm in right now also I'm in office only. But this year I again enrolled as an audit and make sure that I'm attending. Apart from 2 3 lectures, I think I have attended all. So definitely, content wise, it is definitely quite enriching. And also, sir, this Corona and these online classes have been maybe in a sense good for students like us, external students. We are able to join these classes. Otherwise, I definitely
Yeah,
would have missed it.
it's not possible for you to, yeah.
Yeah, so in that sense, even in the when I was there in the what do you call it coursework time, that time also we have a lot of pressure. We cannot join so many courses. But in this Corona time, I have at least enrolled for 2 courses. And though last semester, but I could not attend. So this time, sir, and my PhD was basically plastic deformation and microstructure. So title itself was so tempting. Yeah, I have to join this course. I have to attend. And one of your another PhD student, he also forced suggested me, no, this is the, because I'm a mechanical background. We take an MTech is mechanical only. So he kind of said, ki, if you want to get your basics clear, this is the necessary and sufficient course for you. So, and it is rightly so, sir. At least from the very first class to today, all the basics, so many issues. I mean, be it the crystallography, be it the deformation, dislocation movement. So it was very enriching. And now at least I know ki my basics are okay. I can work upon that. So definitely thanks a lot, sir. And also, sir, not only theoretical parts. I mean, small inputs like what kind of graphs you are supposed to draw. Because in my work, I was drawing, as I might have told you, normal stresses. Then you suggest, it should be shear stress. So you'll get the better this thing. So immediately I'm applying almost whatever I have studied here in my work also. And I hope that that will give me better results. So thanks, definitely. Thanks a lot. Thanks a lot.
Thank you for the encouraging, wonderful words. Okay, I think
Hello, sir.
yes.
Yes, sir. I think everything is said by other classmates. I wanted to what I wanted to say, but sir, I want to thank you that including so much topics within a single course. I think is very highly appreciable. And frankly speaking, that my basic was not very clear. I always found difficulty in defects like line and surface defects and explaining the stress and strain diagram, but now I'm confident enough that I can explain to me and I can explain to others. So
Okay,
thank you, sir. Thank you. Thanks a
thank
lot.
you. Thank you very much. Okay, so I had taken these two from Google. Okay, these two images. I think it's very much applicable to everybody. Okay, even to me also. Okay. So I think I'm trying to learn more and more, and just to see whether I can see more or not. Okay. So I think keep in mind that your first step always will be hardest one. Okay, if you just okay with some activation energy, if you can cross that step, that barrier, so you can see success in your life. Okay. So with this, I think I thank you all for taking this course, okay, and listening to my content, whatever I think the way I tried my best. So I wish you all the best, okay, for all your future endeavors. So please keep in touch, okay. So if you whenever you get an opportunity, you come to my office and you can meet, you can discuss things. Okay. So feel free to come to my office whenever, okay, or feel free to contact me also. I guess all of you have my mobile number. So whenever you need anything, okay, just you can contact me. Okay. So with that, I think I thank you all. Okay. So I'll stop recording. Now I want to hear any negative feedback. Okay. So I think it will not go into, okay, anything. So far I heard a lot of positive things. Now it's my, okay, I think I must also know, okay, the negative things, what I should avoid, okay, while teaching. Okay. So